Hello everyone, welcome to Lecture 6. My name is Başak and from now on, I will be your lecturer. Real-time model serving is a key part of ML systems. It allows you to expose your trained model through an API for a real-time inference. It empowers use cases like recommendation systems, fraud detections, or chatbots that requires instant decision based on a fresh data. This lecture, we will cover deploying model serving endpoint. But first, let's have a look at what we have learned so far. We started with fundamental MLOps principles, what tools and functions Databricks offers us. Then, we have seen some best practices on how to work locally while developing ML applications with Databricks. And then we moved on to MLflow basics, how to train, log, and register models in Unity Catalog. Last lecture, we showed different serving architectures. If you haven't seen Lecture 4 yet, you may want to check it first as we will start from where we left in that lecture. In Lecture 4, we have registered a basic model, MLflow model, which has built-in flavor, and then we registered a custom MLflow model using Python, which gives us the flexibility to implement any logic we want or change the payload. So this lecture, we will deploy an endpoint for the models that we registered, send some example requests, and then see an example of A/B testing. Both models registered in Lecture 4 can be served using model serving module that we will introduce today. But first, let's start with theory. Databricks Model Serving is a fully managed serverless solution that allows you to deploy MLflow models as RESTful APIs without the need to set up or manage any infrastructure. It is super easy for deploying registered MLflow models. It has automatic scaling even all the way down to 0 when there is no traffic. It comes with built-in monitoring directly in the Databricks UI, where you can track latency, throughput, and error rates. And it supports both batch and real-time inference. It makes the transition from experimentation to production very smooth, and it is ideal for teams who want to focus on building great models without getting bogged down in infra concerns. And since it integrates directly with the MLflow model registry, everything just works out of the box. But it also comes with some limitations. First, you cannot choose the runtime environment. Databricks handles that for you. This can be a constraint if your model depends on a specific library version or runtime behavior. Second, you have no control over the underlying cluster size. For example, a single replica is limited to 4 GB of RAM, which may impact large models or requests that require more memory. That said, you can choose the workload size, which determines the number of compute units allocated per replica. Databricks offers small, medium, large, and on request, extra large options like XL, 2XL, 3XL, scaling all the way up to 512 units for more demanding use cases. Additionally, if you enable scale to 0, the serving endpoint can scale down to 0 replicas when it's idle. The lower bound for each workload size becomes 0, which helps save cost in environments where the usage is intermittent. Let's look at some compute units and performance limits. Each compute unit in Databricks Serverless Serving can handle one request at a time. So if you receive multiple concurrent requests, multiple units will be needed, even if each unit is underutilized in terms of CPU or memory. Databricks uses auto-scaling based on unit demands, not based on CPU or RAM usage. This means even if a unit is only used, let's say 5% of its CPU, Databricks may still scale up if more concurrent requests are coming in. The number of units needed is calculated using a very simple formula. Required units is equal to query per second times model processing time. Let's see this in an example. If you are serving 1000 queries per second and your model takes 20 milliseconds per request, that's 0.02 seconds, then you will need 20 units to keep up without delay. And there is a hard upper limit to this. A maximum of 512 units can be allocated per endpoint and per workspace. So the maximum achievable QPS at 20 millisecond latency would be around 25,600. Databricks is using MLflow behind the serverless endpoint, and it supports different dictionary payload structures, which you can see in this table. And we will also see some examples in our code base. Now, let's create serverless endpoint using custom model that we registered in lecture 4. This is my VS Code, and I open my repository. I am connected to my Databricks workspace through VS Code extension, which actually uses DB Connect. I'm using serverless cluster, and I activated my Python environment. So I have a good base to start. So far, we have covered several lecture scripts. In this lecture, I am walking you through Lecture 6, Deploy Model Serving Endpoint. This will be our main entry point. We are also introducing a new module, which is Model Serving class. This will give us some functions that we will run from our main script. For this code to run locally, we also need to make some environment variables available. So in my .env file, I define Databricks token and Databricks host, which are must to have. And I also have a profile, which is optional unless you use default profile. Let's get Databricks token first from our workspace. We are in the workspace and we need to go to our settings, profile settings. Under profile, you will see a developer section. Here you can manage all the accesses because you are the admin of your workspace. And here you can simply generate a new token by giving a name and hit the generate button and it will give you a new token. You can simply copy this and paste it to your environment file. Now I define all the environment variables. Let's start running the cells. I start with importing all the libraries that I need, including my custom modules from model serving class. And next I get the environment variables. If this is running in Databricks environment, DBR token is available through dbutils and Databricks host is available through Spark config. But I am not in the Databricks environment, so I simply get it from my .env file. Next, I create the model serving instance by passing some variables. The model name that I want to serve and the endpoint name that I want to create. I initialize this model instance. Now I will run deploy and update model serving endpoint. But let's have a look at what this model serving class offers us. This is the class where we wrap all the logics that we need to deploy an endpoint. We define a getLatestModel helper function, which retrieves the latest model version of a given model name. It is using MLflow client and getModelVersion by alias function. And then I have deploy and update serving endpoint. First, we check the endpoint if the endpoint already exists. We do this by listing all existing serving endpoints in our workspace and seeing if one matches our desired name. If the user specified latest as the version, then we fetch the actual latest version using our helper method getLatestModelVersion. Otherwise, we just use what they are passed in. Next, we construct a list of entities to serve. In our case, just one model. We specify the model name, the model version, and the scale. And finally, we check if the endpoint already exists. If it doesn't, then we create it from scratch with the given config. If it already exists, then we update its configuration to point to the new model version or change parameters. So let's go back to our main entry point and run model deploy or update model serving endpoint. In my interactive cell output, I see that the latest model version is 2. The very first time when you create a serving endpoint, it will take 5 to 10 minutes for endpoint to be ready. Since I already created this one, it says ready, so I can create some sample records and hit the endpoint. Let's do that. I'm back to my notebook. I create a sample set, sample records to be used in the payload. I use the test set to create my sample records. Here I define the required columns, which are the features that my model expects. Another trick I have to do here is replacing none values with none, which will be serialized as null in JSON when we send the payload to the endpoint. And here is you see an example data frame record in the request body as a list of columns and values. Here I define a call endpoint function, which calls the model serving endpoint with a given input record. It takes the host name from environment variables, and then it creates the serving endpoint name. This is the serving endpoint name that we just created. And then it simply sends a post request. So let's run this and wait for the result. Since my endpoint is configured to be scaled to 0, the first time when I hit the endpoint after creation, it will take some time to actually spin up the nodes because it was scaled down to 0, now it is coming back. But the next calls will be much faster. There you go. We get the response status 200 and this response text. If you want to send more requests in a for loop, you can also simply run the cell, and then you will keep seeing the responses from each call. While this is running, let's also look at our serving UI. Here we see the entity that we are serving and its version. We also see the workload size, which is small. And these are the monitoring dashboards where you can see the request error rate, CPU usage, latency, etc. This is how it will look like when you send more requests to this endpoint. Another important thing to do already is enabling inference tables. By default, the inference table is not enabled. In order to enable inference tables, you need to click Enable Inference Tables, define your table location, and hit Update button. So for me, it's already enabled, and this is the path to the table where I can see the logs of my payloads. Databricks model serving endpoints support traffic splitting. You can go to Edit section and list all the entities that you want to serve. You can also assign different percentage of traffic to each entity. You can configure this on the UI or you can use the SDK. But the split is random. And because of its non-deterministic behavior, we don't really recommend using it, especially not when a consistent routing is needed for A/B testing or user-level model selection. So now we're going to see an example of A/B testing in a deterministic way. Let's quickly remember what A/B test is. A common misconception is that simply splitting traffic between model versions qualifies as A/B testing. But that is not accurate. In true A/B testing, a customer must consistently see the same model version throughout the entire experiment. This consistency is critical to accurately measure model performance differences, whether it's a click-through rate, conversion, or other metrics. A naive traffic split, like Databricks build and traffic routing, doesn't guarantee this. One user might hit model A on one request and model B on the next, especially if the requests are stateless and routing is random. To run reliable A/B test, you need a sticky assignment strategy, like a hash-based split on a stable identifier, could be user ID or session ID. That way, each user consistently gets routed to the same model variant for the entire test period. In our example, we will use two different versions of an MLflow model, and they will be combined into a main PyFunc model that serves as the core model for our endpoint for A/B testing. Now, let's see an example A/B testing implementation. For this part, I am walking you through Lecture 6 A/B testing.py notebook. We are also going to use the basic model class that we have seen in lecture 4, which has all the logics implemented in it: loading data, preparing features, training, logging, and registering model. We will use these functions in our A/B testing module. I start with loading my imports, which initializes the interactive session. Then I create Spark session, load my environment variables. I get the config. Here are my catalog name and schema name. And in the next cell, we are going to create a basic model, which will load the data, prepare features, train, log the model, and register a latest version. Here we see the output. It is taking a while. All right, we have the experiment. And we registered the model. Let's have a look at our workspace. Okay, this is the experiment that we just executed. And let's go to catalog, MLOps dev, catalog, Marvel character schema, and the models. All right, we just registered version 6. Nice. Let's now create a model B, which will use a separate parameters, different parameters. This will be our model B. It is following exactly the same logic: loading the data, preparing features, training, logging, and registering model. This time, we are registering Marvel characters model basic B. So this will be the name that we will see in the UI. We are seeing all the outputs written here. All right, the experiment is there. The UI can be flickering sometimes. There you go. This is the experiment we just executed for our model B. And we also just created version 1 of model Marvel characters model basic B. Let's check it out in our catalog. Marvel characters, there you go. We just created Marvel character model basic B and registered version 1. All right. What we are going to do next is what I showed you in the slides. We will define an A/B test wrapper, which will take model A and model B as an input, and it will use both depending on the ID. In the predict function, we are defining which ID should be routed to which model by using simply a hash function. It works by taking the ID from the input data, hashing it using MD5 and converting the hash into a number. Then it checks whether that number is odd or even. If it is odd, it uses model A. If it is even, then it uses model B. This way, the same ID will always be routed to the same model. We also remove it from the model input because the model does not need the ID. So this is a predict function that we define in A/B test wrapper. In the next cells, we are going to register this model. Let's start with loading the train and test set. Here we create an experiment. We pass the model name, create the wrapper model instance, and we start the MLflow experiment run. This will take model A URI and model B URI as an input while loading the context. Once this experiment is completed, we will create a new model and a new model version for the given model name, PyFunc Marvel Character Model AB. Here we see in the outputs that we just created version 1 for model Marvel Characters Model PyFunc AB test. Let's click this and see in the UI. There you go. In my Marvel Character Schema model section, I just created a new model for A/B testing and a new immersion. The next is we will create a model serving endpoint for this specific MLflow model using the workplace client. It has the same logic as we've seen in model serving module. We define the serving entity, which is just one model, and this is the model endpoint name that we pass in the config. Since we already run this, we should be able to see in the UI that our endpoint is getting ready. There you go. So this is the endpoint we just created. And as I mentioned earlier, it will take some time to make this endpoint ready. My endpoint for A/B testing is ready. So now I can create some sample records and hit the endpoint, just like we did earlier. So I create some sample records. This is how a sample request body looks like with the feature names and the values. And I run calling the endpoint. There you go. I see the response, the prediction and the model that is used. We can also send multiple requests where we get to see which models are being used at each response text, and also the prediction, whether the character is likely to be alive or dead. This is the end of A/B testing. This lecture, we learned how to deploy a model serving endpoint for MLflow models registered in Unity Catalog. And then we've seen an example of A/B testing using MLflow Python as a wrapper class. Next lecture, we will talk about Databricks asset bundles. See you there!